And you can imagine how numerically horrible it is when you do that. So if you have a high-dimensional problem, if you just run this, it doesn't work. And they have all sorts of beautiful tricks to make it work. I mean, I could go on with that, but it would just be, just naming definitions of that. Naming words without definitions. But then there's a whole thing here, as I mentioned before, of when it is well conditioned, numerically stable, and the most basic thing is when do you forget the initial estimate? Because we all know that when we initialize this algorithm, our initialization is junk, and so there's a question of robustness, of stability of the algorithm. And luckily that is completely resolved under minimal conditions. It doesn't matter if you use the wrong initialization for this algorithm. It'll forget the initial condition, everything will work. That's really nice. And that's not known for any other way of filtering. It's only the common filter where we have any theory to robustness theory. It's very strange that, thank you. I guess I could blab for hours. In the Gaussian case, there is, I'm glad you slowed me down. So fact number one, naturally, you get rid of the hat, right? Okay, so first of all, it becomes a an actual expectation, okay? Conditional expectation. What's remarkable is, guess what happens with these guys? So I've been saying all along it's a covariance. It turns out to be conditional covariance. Why do I make such a big deal about that? It's mind-blowing in the sense that this, we all know, and you all know because you've reviewed the quiz, that a conditional expectation is a nonlinear function of the observations you're conditioning on, so it's a random variable, right? But if you look at the, but we defined it as a covariance, so it's not random. Yeah. So even though this is it turns out for the Gaussian case it's a conditional covariance, but it's deterministic. All right, so if you're sort of one of these people who's in the machine learning world, you'll hear over and over again, exploration versus exploitation, blah, 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 blah. There's no exploration needed because it doesn't make any difference. You can't say, hey, why don't I make a larger signal so I can excite the system and see what's happening? It doesn't make any difference. It doesn't matter what you do. This would still be true if I had an input, anything at all. There's nothing you could do to learn better. Your error covariance is independent of your observations. That's amazing. It's not going to happen for anything else besides a linear Gaussian system. It's completely special. And we'll talk about later, I think, yes we will, talk about cases where this is severely violated, where this is extremely sensitive to your measurements. Okay. All right? So those are two big facts. And if it wasn't for you're slowing me down. I would have forgotten to mention them. Anything else?
Are there any rival filters?
Oh, well, rival filter, this is optimal, you know.
So nothing can compete with it?
Yeah, no, the thing is that I'm not an expert, but when in high dimensions, there are books about how to make this more robust, you know, make it more numerically stable. You know, basically how to sort of bring it down to size. But that's way beyond my expertise. So, yeah, now this is it. If you've got a linear system, this is all you've got. Yeah. And if you've got a nonlinear system, you just pretend. You know, there's something called the extended common filter, and you linearize on the fly, and you just apply the common filter, and 99% of the time it works. It's just, which is so disappointing because nobody knows why. There's so few papers out there with explaining why the extended common filter works, but it's often used. You know, this is an absolute frontier filtering. I mean, I'll be saying this again later. When you get outside the linear domain, you're just in the desert. It's just, it's awful. This is fun. Anything else? Yeah. All right. So, I erased my system. Okay. All right. So, new topic. I said in the syllabus I was going to do Carhoon and Loew expansions. I'm not, but I'm going to give you the main idea. Okay? It's a beautiful subject. And I love to present it just because it gives you such a different view of stochastic processes. So to me, this to me is how I usually think of stochastic processes. You know, I have some black box, noise comes in, and observations come out. You know, and for me, I'm a control person, so I'll have inputs as well. You know, so UK is something I get to choose. This is maybe, I've got a controller here. And I take my state measurements and I use those to synthesize a control law, put it into here, and things come out. So you're used to thinking about that's how the world works. You know, there's fresh noise that comes in and new things happen. A blast of wind hits the, you know. You think of causality as part of the whole business, all right? That's one way to think about stochastic processes. So this sort of causal view. Why am I using blue for that? So, you know, something you can never forget is there's no such thing as a random anything. There's nothing random in this field, okay? You know, random exists in maybe life, but it doesn't exist in this field. So omega gets chosen once and never again. There aren't repeated omegas popping out. There's one omega, and that's the end of time. All right, you know, this capital omega was invented at the you know, the birth of the, you know, the solar system, and I guess there's a universe as well. And at that time, an omega was picked, and you're all a function of it. That's what Kolmogorov declared that at the beginning of time. Yeah, it's so hard to, you know, it's so hard to remember this. This is the model. It's really weird. So this kind of viewpoint, you know, obviously is not the only one, because all of this is a function of one omega. All right. So for example, take a bunch of, let's consider continuous time. I want R. Oh, not R. So I'm going to get into a bit of representation theory, a lot like Fourier series representation theory. So it's really convenient to have complex valued everything. But these functions are just functions, okay? So they're just, complex valued functions from 0 to t. And we're going to define a norm on functions. And I'll, if I really want to emphasize it, I'll write L2 of 0t. This is the L2 space of functions on 0t. And an inner product as well. Okay. So these are nothing random, okay? Now then you give me a bunch of random variables. So the only randomness goes to the coefficients, okay, and they're complex valued as well, because it's just like this is sort of like a Fourier series way of thinking, all right? And this is a stochastic process. So the CKs is a CK of omega, right? So that omega that was picked by Kolmogorov billions of years ago at the dawn of the universe. He or she chose that omega, and it's never changed. All right. So what you're doing is you're taking that omega, and then you're plugging in for coefficients. And if you knew omega again, you'd know this function for the entire horizon. I'm making it a finite horizon for simplicity, and of course it could be infinite. All right. Okay. Cool. Now, it makes things a lot easier if you choose an orthonormal basis. Basis. I use the word basis because in the end we're gonna make sure that these functions basically span every possible function in L2. So forget that I said the word basis. Let's assume they're orthonormal. You can imagine it makes it a lot easier to think about things. Like, why would I care about that? Well, it makes it really easy to get the CKs, for example. Suppose you just gave me the process. How would I find the CKs? I would just take this x of t and I would dot it. Well, this, unfortunately, put an I there. I would take this and I would dot it by fi, and everything would disappear except for the ith element. Okay, so orthonormal is nice because given the process, you can find the coefficients like that. Okay, so I was going in the forward direction, but we're not going to always go in the forward direction. What else do I want to say? Okay. Okay, let's do it. So also, if you look at this will be more interesting. If you look at these are random variables. If we looked at their cross correlation, or cross, they're not necessarily zero mean, but yeah, cross correlation, it would just be defined by that expectation. And if we plug this all in, it's pretty ugly, right? Everything's scalar valued here. So if I take this star, if you look at the definition, if I star this, I just flip this around. So I flip the dot product. And then if I plug back in the integrals, I'll get something interesting. That's a star. So this first one, there's a star for the fi, because that's how I've defined it. And for the second one, there's a star in the x. All right, so there's a double integral here. And I can take the integrals outside the expectation if everything is well defined. If all the integrals are finite, take an analysis course, you'll see that. Okay? So under these L2 assumptions, I can take the integral outside. All right? And what am I left with? Everything here is these guys are deterministic. It's only the x's that are random. So I get that, right? And that's just a covariance matrix. And if I integrate over S first, I can do this. So I'll slow down now. I wrote this down, I'll explain. I'm going to call this K for the autocorrelation matrix, okay? I haven't assumed anything zero means, so it might not be covariance, it might be correlation, I don't know. Can you see what I'm doing here? I've got my autocorrelation matrix here. Matrix, it's an infinite dimensional matrix. T and S take on continuous values. And then what I'm sort of doing is I'm taking this and I'm integrating over S first to define a new function. Okay, so I'm thinking of so this function of two variables is called a correlation function. I think of it as a mapping from L2 to L2. So given a function f and L2, L2 on the line, these are deterministic world, you tell me, what do I mean by kf? If I write g equals kf, what do I mean? You can sort of see what I'm getting at here. Remember, I integrate over s first. So what's g of t? Well, it looks like it would be the integral of kt to s, f of s ds, from 0 to t. All right, so when you go through this and you look at the correlation matrix for the coefficients, it turns out to be a dot product in this infinite dimensional space, as you see here. All right. So this is just basically moving things around. So I integrate over S first, and I got the integral of this function of t and s. It's called a kernel times fj of s. That's what I'm denoting that abstractly as k times f. It's just like matrix vector multiplication. Instead of integrating, instead of summing, I'm integrating. All right? And so you can do this. So there's two messages here. Cool. There's two messages here. One is just, again, this thing in your mind is there's two ways of expressing stochastic processes. There's a causal view, which is the most physically natural, and there's this wacky view where Kolmogorov was born trillions of years ago and invented omega, and it never changed. And all of us are just deterministic functions of that. And that is the only model there is, I mean, that's what probability is about. Omega never changes. And so you can do this. You can come up with crazy models like this, where once you know the coefficients, you know the process forever. All right. So the amazing thing is this. The amazing thing is that this is a construction. Why would you do this, right? Well, the thing is you can go backwards. This is what's really awesome. So I don't have to say, I'm going to cook up some functions and then construct a process, and aren't you proud of me? It turns out that every process can be described this way in a way. And I've got time, so we can leisurely explain this. All right? So this is just setting the stage, So if you gave me a bunch of functions again, gave me a bunch of complex random variables, I could define a stochastic process like this. And under this orthonormal assumption, I can retrieve the coefficients, and I know the autocorrelation of the coefficients from this formula. All right. Okay, so you give me a second order stochastic process. It is this. Yep.
Well, just out of curiosity,
Yeah.
I'm just trying to get my head wrapped around this.
Yeah.
The problem line you gave in the assignment.
Yeah.
CK, in some sense, our Brownian motion.
Yeah.
Okay, so and then you have instead of summation and integral.
Yep. So this goes on forever. So here I had a finite sum. And what I'm going to show you is that when you do this in the most natural way, this is 0 unless I equals j. So it's white noise. So basically the most elegant representation turns out to be where the coefficients are white. Okay? And if you go from a finite interval to an infinite interval, you have to give up on sums. And you have to integrate white noise. And the only, what we mean by white noise is that dB of t, where b is Brownian motion. Yeah. So I'm presenting sort of a baby version of the coherent law of expansion. The full one is it's not any different than what I'm doing here. It's just a measure theory that comes up, which I don't want to get into. So when you look at a finite time horizon, everything is really fast. So you give me a stochastic process, I can represent it in this way. I'm going to show you how x of t. Hold on a second. So I'm going to define the autocorrelation function. Continuous. I know we don't need this, but let's assume it's continuous. So it's continuous as a function of t and s on the square. So t and s take on values between 0 and capital T. And I claim I can construct a stochastic process and actually, I don't want to have to deal with means. Let's subtract off the means, so 0 mean. The mean's not important. I could always subtract it off and then add it on later, right? If it didn't have 0 mean, I'd subtract it off and add it back onto the scope and I'm done. So let's just make sure everything's 0 mean. Let's see, and then. Okay, so this maybe isn't so satisfying because I'm not saying that I can, and this is not an estimate, this is a different notation. X hat just means, I should have used hat maybe. It looks too much like an estimate. I'm just saying I can write down a stochastic process in this way and it has exactly the same second order statistics. And continuous time, that's saying a lot. It's a lot of statistics we're matching up between the two processes, right? And there are, and the construction is principal component analysis. So I'm not going to define what PCA is. I'm not going to explain how these constructions are related, but it's just something to keep in your notes that you'll someday, if you ever work in PCA, or if you get deeper into this, you'll be interested in looking at the connections, because I don't want to, that's a whole other course, okay? So PCA, but PCA is like one of the ways of doing model reduction. And that's one of the goals here, is we'd like to be able to approximate this complicated process with a simpler one. And maybe for forecasting, Because after all, from what I said, if I know these coefficients, I know the process for the future forever. So forecasting comes down to just estimating parameters, if I know these functions.
You can predict the whole future with even a finite number of coefficients?
No. I mean, take a look. You tell me.
Is that your claim?
No. Could I? No, you tell me. No, x of t is equal to this. So if I was missing one, I'd be.
So I'm saying you can't. So you don't need an infinite number of coefficients.
No. Of course you would. Yeah. No, this is the definition, right? So and these guys are uncorrelated. So in order to get x exactly, I would need all the coefficients. But I can get an estimate by estimating them. Yeah. And we also know these CIs are going to decay to 0 quickly, so I can get a good estimate just by getting a finite number. Yeah. All right, let's do it. That's what's so cool. I'll construct them for you. So the question was, where do you get the FIs? All right, so once you get the FIs, we know how to get the CIs, and we know how to check to see if they're white, because these formulas are going to always be valid. It's just once I claim I've got this representation. So here's the crucial fact. There we go. So I can't look at this because I don't have the representation yet. Turns out to always be true that these guys are positive semi-definite. And what I mean by that is if I take any f and, do I want to do that direction? I want to do it this way. If I take kf as defined over there and dot it with f, I'll get something non-negative. And again, that's why I stress, these are functions. Everything's deterministic here. K is just a function of two variables. It's continuous. It just happens to be a correlation. And how do you prove this? You just plug in the facts. All right, so we basically do this and we undo what we did before. So kf of t with what I call g over here, and that's this thing over here. And what am I going to do now? I don't have much to go on here. K is just a continuous function. This can't be true for any continuous function of two variables. I got to go back and plug in the definition. And I find it separates. All right, so I just plugged in the definition of k that's over there, and I pulled the expectation outside, just like I did before, okay? If you pull that, the expectation of that is just that. All right, and I got a double integral. And does that look like anything interesting? It separates, right? It's an integral times an integral, and they're the same integrals except that one's the complex conjugate of the other. So this is just nothing more than the expectation of one of them. So I can take the t parts to the left, and I could put the s parts to the right, but it's the same integral with the complex conjugate. So take the modulus, square it, and that's greater equal to 0. Okay, so you've got a positive operator in a way, and then there's a whole theory of positive operators in L2, and if we had more time, it would take me 2 more hours to give the complete proofs of what I'm about to say. So does anybody know what I'm going to choose for the FIs? Yeah. As soon as you hear positive definite, you know there's an eigenvector. Yeah. So there we go.